Hello, my name is Danny Nolan and I'm the Director of Chassis Sim Technologies. And welcome to this latest Chassis Sim video tutorial / Dan's Vehicle Dynamics Corner. And today, ladies and gentlemen, we're in for a real treat. Today, what we're going to be talking about is using simulation to get results. In particular, ladies and gentlemen, what we're going to be discussing today is a very abridged version of the presentation I gave at the recent Australasian Alto Engineering Formula SAE conference. And there was a lot of good points that were brought up in there, and this had so much validity that I really wanted to share this with you. So, what we're going to be talking about is as race engineers, what we need to focus on. We'll talk about the process that you need to bring to bear, and then we're going to segue this into where you bring simulation in. Also, too, as a bit of a warning here, ladies and gentlemen, what we're going to be discussing could literally form a 2-day seminar. That being said, one of the key questions that race engineers, vehicle dynamicists always have, what's the process that we need to bring to bear? How do we tie in what we do with hand calculations? How do we tie this in with simulation? It's almost like the question that dare not ask its name on the simple principle that people don't want to look foolish. And one of the great things about that Formula SAE conference is I was able to sort of bring this question directly to light. But also too, ladies and gentlemen, I'm going to be talking around a lot of these points because to do this subject justice would take a 2 to 3 day seminar. But what I want to do is to give you all a framework that you can go about and go, hey, yeah, I can do this. This is what I need to do in order to get the job done. So let's get started. So our two main currencies as race engineers boils down to the following. All car performance boils down to grip and stability. And if you're an unlimited unlimited formula, engine power. However, as race engineers, we will mostly be dealing with grip and stability. And the following, ladies and gentlemen, is the perfect case in point, which is the Supermarine Spitfire. And I just don't mention that because this year is the 100th anniversary of the RAF. I mention this is because one of the true geniuses of the Spitfire is the Spitfire combined grip with impeccable handling. And if anything, it was often said that you didn't fly the Spitfire flew you. And really, if you really want to get a perfect picture, ladies and gentlemen, of what our holy grail is with regards to when we engineer a race car, the Spitfire is a perfect case in point. Now, when it comes to nailing down grip and stability, grip's pretty easy. I mean, within reason, if you've got a mechanical setup and an aero setup, you can take a reasonable stab at getting some deltas of what's going to go on with grip because all you've got to do is calculate tire force. That bit's easy. The tricky thing is calculating stability, and then to that regard, ladies and gentlemen, the stability index is our best friend because as we can see here, with our figure here, what we're classifying with the stability index is the moment arm between the neutral point of the car, that is the center of the lateral forces, and that moment arm to the center of gravity. That is what the stability index is all about. Now, I've talked about this at length on a number of occasions, but let me just sort of give you the quick highlights here. In terms of defining the stability index, all that we're doing with defining the stability index is it's simply the moment arm of your front and rear slip angle slopes. That's all it is. That's basically what all this mathematical gobbledygook means. Now, you can find the derivations of this in some former tutorials I've done. You can also find this in my book, The Dynamics of the Race Car. But bottom line, this is your approximation for stability index. Now, what does the stability index mean? Less than 0, the car's stable. You give it a disturbance, it'll write itself out. If it's 0, you give it an input, like you give it a quick steer input, it just wants to keep on going. If it's greater than 0, you turn the steering wheel, the car wants to swap hands. Rough rules, that's pretty much a very good rough rule of thumb of what the stability index means. Now, here's the thing about the stability index. The better the driver, the closer they can tolerate a car being close to 0. That is, so rough rule of thumb, gentlemen drivers will probably be gentlemen drivers will be quite happily tolerating a stability index of about 10%. Your your Ayrton Sennas, your Michael Schumachers of this world will / Lewis Hamiltons will quite happily live with a car between 5 to 2. So that's really one of the key reasons why they've got that ability to go out and find that extra grip, because they can put up with that borderline stability. Now, rough rules of thumb to get going. Good start value for the stability index is about minus 0.05 or about 5%. So the moment arm between between the neutral point, the center of lateral forces, and the center of gravity is 5% of the wheelbase. Okay, another rough rule of thumb too. You can tolerate the occasional exertion to 0.1, but you don't want to go too much over that. Howbeit, just remember that is a rough rule of thumb. Okay, so why the stability index? If we take a look at the simulated change of a Formula 3 car where we have a baseline change and we move the aero balance 5% forward, and because this is a simulated change, if you take a look at the steer, RPM, your steer inputs, your velocity inputs, your throttle inputs, there's there's not a lot of change. However, where it truly shows up here is in the stability index, and this really underscores why stability index is such a powerful measure of car stability, because it allows you to see really into the heart of what the car is doing. Okay, so having said that, how do we tie stability index and grip together? Well, to do that, our first port of call is the lateral load transfer at the front. Now, this is sometimes referred to as the magic number. Now, look, this number doesn't have any paranormal or metaphysical implications to it, but where it is very, very powerful is it gives us a very, very good first cut of seeing what a given setup will do. This derivation here is something I've discussed in my race car engineering articles. I also discuss it in my book, The Dynamics of the Race Car. But it's a very, very good rule of thumb. Now, the thing about using lateral load transfer at the front, yes, it's all based on static approximation. So it's a first cut. This is not the be-all and end-all of what you will sacrifice everything on the altar of car setup to. However, what it does do is it gives you that first cut of what the grip is going to do and how the stability index will go for a given lateral load transfer distribution. So this is sort of like your first port of call to trying to nut out what a setup will do. And one of the great things about this is that when it gives you the ability to plot grip versus lateral load transfer distribution. And I've done that here for 2 different tire compounds. But more importantly, it allows you to evaluate what's going on with the stability index. And that, ladies and gentlemen, is something exceptionally powerful. And I term this the mechanical grip balance equation. And the great thing about the lateral load transfer at the front is that this gives you your first cut. Even though it's pseudostatic, it gives you your first cut of doing this and this, which is why this is always your first port of call in terms of figuring out what a setup is going to do. However, in order to do this, we need to be able to create a tire model. Now, when we talk about creating tire models, most race engineers, vehicle dynamicists, and most punters in motorsport engineering usually throw their hands in the air, scream blue murder, and run for the nearest exit. Now, ladies and gentlemen, in order, believe it or not, getting a tire model ain't that difficult. And let me just slightly recap creating tire models from scratch. Now, the key in understanding a tire model, ladies and gentlemen, is understanding this equation here. Traction circle radius versus load characteristics. Traction circle radius is the initial coefficient of friction, 1 minus kb times fz, where fz is the normal load. Think of that, ladies and gentlemen, almost like the tire equivalent of the quarter car damping model for springs and dampers that we'll talk about very shortly. Now, the upshot of this, ladies and gentlemen, is that we can describe every tire in terms of the load at which it generates its peak grip and the peak grip itself. And that peak grip is the initial coefficient of friction times times the peak load divided by 2 and LP. If you can understand that, ladies and gentlemen, you are well on your way to truly understanding what a tire model can do. Now, in that tutorial, creating tire models from scratch, which I talked about in an earlier chassis sim tutorial, your first port of call is going through looking at your tire loads. And you can look at that either using track data or using the chassis sim track replay facility. It really doesn't matter what you do. But here's the key point, ladies and gentlemen. As a rough rule of thumb, you take about 100, 200 kilos on top of that peak tyre load. For an F3 car, you go about 100 kilos. For a Formula SAE car, you probably go about 30 to 50 because they're much lower weights. Something like a GP2 car, a V8 supercar, and an LMP2, LMP1 car, you'd go about 100, 200 kilos. And that's really and what that does is it just gives you that first stab of what the car is going to do. Now, your next point is you need to know the force you're going to produce. And typically what you do is you take your peak cornering speed and its peak curvature. And what you do is you plug that in to an Excel sheet like this. Now, what I'm going to do as a bit of a treat is in the link in this description, I'm going to give you a link to the Chassis blog where you will find a downloadable version of that sheet that you guys can play with. That little Excel sheet is a little bit like the Millennium Falcon from Star Wars. It doesn't look like much, but it's got it where it counts. So don't leave home without it. So once you're done with that, you can plug that into the Chassis Tyre Force Modeling Quick Start, and that, ladies and gentlemen, gives you your first cut of your tyre model. Is it perfect? No, but I can tell you right now, ladies and gentlemen, we started to introduce this into the Chassis community in 2015, and it absolutely revolutionized the ability for us and our customers to derive tyre models very, very quickly. So don't fall under the excuse, oh, we don't have tyre data, therefore we can't create a tyre model. That's complete and utter nonsense. Because once you've got that, you can then, and here's the power, ladies and gentlemen, once you've got that, you've now got the ability to evaluate your grip and your stability index versus lateral load transfer distribution, ladies and gentlemen. So that now gives you the ability to actually derive a setup as opposed to spotting your finger in the air or just blindly using a computer-aided engineering tool like Chassis. It gives you a feel for the numbers, ladies and gentlemen, and that is something that is very powerful and very profound. Okie dokie. Right. So our next stage in the process is selecting springs, geometries. Is selecting our springs and geometries because that will affect our tire heating. Now we can do that via using the track replay simulation with Chassis, where we turn the internal temps on, or you do it via testing. It really doesn't matter. But once we have that, our next port of call is to use damping ratios. Now this, ladies and gentlemen, is something in the damper workbook on the Chassis blog, in my articles on Racecar engineering, and in various tutorials I've given on the Chassis YouTube channel. Is something I have done to death. But let me give you some clear highlights here. Number one, you use the quarter car model. Number two, you use your spring. Your wheel rates in spring and dampers, and these are your two major currencies you'll be using. The natural frequency, and that will be in radians per second, and your damping rate, which you can make as a function of damping ratio. It's something very, very powerful, ladies and gentlemen. Also too, and I know this will annoy my friends in North America, but oh well, I really don't care. Use strict SI units. I cannot stress enough. This is your fundamental building block when it comes to figuring out dampers. Don't leave home without this. Now, again, just to sort of quickly summarize what you need to be looking at, here's my damping ratio selection guide. Rough rule of thumb, in your low speed, you stick to about 0.7 to 1. Sometimes you might creep up to 1.3, depending on the level of downforce that you're dealing with. In the low speeds, in the high speed section, you're traversing over the bumps, so you want a low damping rate, so it will traverse over the bumps. It'll traverse over the bumps nicely. There's some rough rules, and they are your rough rules of thumb. Let me just leave that there for about 10-20 seconds, so you about 10 seconds, so that you can appreciate that. Just I'll see you in about 10 seconds. Okie dokie. So once we've got our damping ratio, once we've calculated our lateral load transfer distribution, once we've determined the tyre model, and once we've done our springs and our damping rates, This is where our simulation tools come into play. And our first port of call is the shaker rig simulation. Make no mistake, ladies and gentlemen, this is one of the most powerful toolboxes you will ever use in chassis sim. Because one of the great things about this toolbox is it allows you to understand both contact patch load variation and the response of the car in the frequency domain. Now, I have presented a tutorial before about how you go about using this. So let me get straight to the highlights of how you employ this. First things first, you select a corner speed that you're most interested in. So it can be a medium speed corner, say like 150k an hour or a 200k an hour corner. You put in your peak input velocity. Rough rules of thumb, you take your damping velocities divided by 3. Again, rough rule of thumb, it gets you in the ballpark. And then you export your file name. This is how you use it, ladies and gentlemen. First things first, you're looking at the frequencies. It tells you where the resonant frequencies are. It's your bellwether of what you need to be looking for. And when tuning, you start tuning for minimum CPLs, and you focus on springs, bump rubbers, and the noders. That being said, your springing is always fundamentally going to be a function of aero and tire heating. So you don't want to go too stupid with it. Then you'll play with the damping response to get the CPLs you want, and then you play with the damping shape to get the response that you want back in. But one thing I cannot stress enough, you don't go stupid with this. It is very, very easy to get lost. Once you're done with that, that's when you enter it with lap time simulation. Now, these are pretty much my 6 commandments about how to use lap time simulation. Rule number 1, you log simulated data as per race data. Rule 2, as per running data, you make a record of it. Always without fail, you look at the data and you look at it critically. You just don't rely on lap times. You only do global sweeps once the model is sorted, and you focus on small, sensible changes. But you're looking for small and consistent consistent changes. And what I mean by that, ladies and gentlemen, is something like this. So that's our C time. No huge changes, all nice and consistent. I cannot stress that enough. The other thing too, and I talked about this at length in my tutorial and Racecar article about how to look at simulated data. I cannot stress enough, ladies and gentlemen, that you've got to look at simulated data with a slightly different lens to actual data. And what I mean by that is that because the fact that chassis sim always knows where the grip is, and because it's like the Terminator, it does not know fear, it does not know mercy, and it will not stop until it goes as fast as possible. Your changes are not going to be exhibited in huge changes in steer and throttle. They're going to show up as cornering speeds. That's the thing you've got to look for. And so here are some rough rules of thumb to go by. 0.1 to 0.2k an hour is a mild change. 0.2 to 0.6 is a moderate change. 0.6 plus is an extreme change. Now, the other thing that I also want to make very, very clear, ladies and gentlemen, is what to focus on with correlation. Ladies and gentlemen, if I had $5 for all the people I've seen who have wasted months on getting the perfect correlation, ladies and gentlemen, I would not be giving this tutorial today. I would be retired as a multi-millionaire in a subtropical paradise, surrounded by beautiful, intelligent, drop-dead, gorgeous young ladies who would want to have their wicked way with me every day. However, I'm speaking with you fine people today. So, one point I want to stress about correlation. It's a consequence. It's not the end goal. Correlation comes when you've evolved your tire model, when you have evolved your aero model, and you've measured your car, you've collected the data properly. It is a consequence. It's not the end result. That point, ladies and gentlemen, that I've just stated about correlation, I cannot stress that strongly enough. So here are some good rough rules of thumb to go by. 80 to 120 for road course use, 80 to 120k an hour. If you're within a delta of 1 to 2k from actual v simulated, that's good enough. 120 place 160, 2 to 3, that's fine. 160, free, anything over 160 is about 3 to 4k an hour. The exception, ladies and gentlemen, that proves the rule are ovals. And because with ovals, getting the tire loads matched is absolutely critical for what you'll do in your simulation work. So with ovals, you've got to be a lot more fussier on the correlation. That being said, What you're seeing here, actual data is coloured, black is simulated, is an example I did with a amateur driver on a VDV card. Now, the basis of that correlation, ladies and gentlemen, was more than sufficient to make significant headway with that team study of suspension geometry and damping rate. So I cannot stress that enough. Okay, conclusion and some parting thoughts. First things first. What we've talked about here, ladies and gentlemen, is your process of how you go about engineering and race tuning a car. Now, a couple of points I want to make, and I realize this is violating Presenting 101 because I'm going to introduce some new points right at the close. I cannot stress enough, you always measure up the car and you prepare the monster file and calibrate the data. Let's put it this way, in the chassis sim boot camps, those 2 points I spend at least an hour and a half on, and that is no accident because the old thing in, garbage out. You then evaluate the tire model. You understand your lateral load transfer at the front to generate the mechanical, your grip balance equation. You select your springs and geometry to get your tire heating. You choose your damping ratios. That's when you work in with refining with the shaker rig and lap time simulation. But just remember, ladies and gentlemen, you will always, our 2 jobs as a race engineer is grip and balance. And with what I've just presented to you, even though I could have done a 2-day seminar on this, what I've just presented with you is the framework of which I go about race engineering a car, and I trust that this will prove something useful to you. Let me conclude on that note, and I look forward to catching you all in the next chassis sim tutorial and the next episode of Dan's Vehicle Dynamics Corner.